Hello everyone, I'm Huan Gao from Institute for AI Industry Research, Tsinghua University. In this video, I'm gonna present our poster paper to ICCV 2023, DQS3D. In this paper, we consider the task of semi-supervised 3D object detection, which aims at reducing annotation overhead for complex 3D indoor scenes. Our contributions are threefold. First, we shed light on the superiority of dense matching over proposal matching in semi-supervised 3D object detection, which could not only harvest more pseudo-labels but also improve the pseudo-label quality. We proposed the first framework for densely matched quantization-aware semi-supervised 3D object detection, where we point out the problem of quantization-aware and come up with an on-the-fly fix to it. We conduct extensive experiments on public datasets and achieve significant results. For example, DQS3D scores 48.5% MAP at 0.5 on Skynet using only 20% of data, while the best published result is 35.2%. Following prior arts, we adapt the robust self-training approach for our densely matched semi-supervised learning framework as depicted in this picture. The framework includes two identical but independent networks as the base detectors, which are implemented by FCAPS3D. During training, an input batch is composed of both labeled data with ground truth object annotations and unlabeled data. The input batch is then augmented by a symmetric quantization-aware transformation, which consists of a random rotation around the upright axis, random translation, and the quantization-aware correction. The augmented and unaugmented batches are then fed into the student and the teacher modules respectively, producing voxel level predictions. The teacher predictions are then aligned to the student predictions with the same transformation, resulting in the transformed teacher predictions. With the same transformation, the dense matching between the two sets of predictions is naturally established, which is further filtered to increase the quality of pseudo-labels. The student network is optimized by enforcing a consistency loss on the remaining match set and a supervised loss between the student predictions and the ground truth labels. In this figure, we illustrate two matching schemes. For proposal matching, each teacher prediction is matched with the student prediction whose center is closest to that of the teacher prediction. And for our dense matching, the matching is established through spatially aligned voxel anchors of dense detectors. In this picture, we shed light on the problem of quantization error. We identify the problem of quantization error as that the voxelization operation and the data augmentation operation like rotation do not commute with each other. This leads to the spatial location of an input point cloud corresponding to different ones after being processed by the student network and the teacher network, respectively. As a solution, we derive a closed form composition rule and implement it on the fly, which leads to consistent performance gains in various settings. We conduct transductive analysis on different matching schemes in semi-supervised 3D object detection. Experiments are conducted on Skynet with 10% of training data equipped with labels. From this figure, we can see that compared to prior arts, our approach can harvest more and better pseudo-labels. More and better pseudo-labels lead to consistent performance gains in various benchmark settings. We report the performance of DQS3D and the prior arts in both semi-supervised and fully supervised settings on the Skynet and the RGBD datasets. We can see that our method outperforms prior proposal matching methods by large margins and sets new sorter results on the semi-supervised 3D object detection benchmark for both datasets. It is noteworthy that the improvements of MAP 0.5 is generally larger than those. It is noteworthy that the improvements of MAP 0.5 are generally larger than those of MAP 0.25. We attribute this to the denseness of the pseudo-labels, which provides more spatially fine-grained supervision for the student model. And that's all for our presentation. Thank you for listening.